Hello everyone. So as you said, I am Sultan and I am a consultant at Tetrel Security. I'm based in Montreal. I used to be in Waterloo, Ontario, moved there recently. My specialty is embedded system security and wireless communications, things like looking at firmware and ROMs and looking at protocol stacks and sometimes a bit of reverse engineering of protocols as well, and other wireless messing around with things. Bluetooth's been something I've been interested in for a long time now. Some of you may know Sniffle, which is a tool I released some years ago, which is a tool for Bluetooth low energy sniffing. It's all open source. Later I'd worked to extend it with functionality for transmission and built on top of it a tool for performing link layer relay attacks on Bluetooth low energy that allow more efficiently relaying connections with low latency and doing so in a way that works with encrypted connections where the keys are unknown. So in today's talk, I'll be going into a new feature, or a relatively new feature of Bluetooth called channel sounding. So channel sounding, which was introduced in Bluetooth 6.0, is a feature that allows determining the distance between two Bluetooth devices using the signal propagation time. It aims to provide secure distance bounding between devices using measures with pseudo-random values based on a shared secret to block attempts at spoofing devices. It's designed for applications that require securely determining distances between devices and preventing people from impersonating devices being closer together than they really are. One common use case for this is phone as a key systems. For example, if you want to walk up to your car and you want it to unlock when you get close to it, you don't want an attacker to be able to fool the car into thinking that you're nearby when you're really not. Same thing for, say, accessing a house or going into a building. There are other applications of channel sounding too, since channel sounding enables substantially better precision in distance than past approaches. So it's also useful just for localization to figure out where a device is within an environment. And while people have been doing secure bounding for a while with ultra-wideband, it's relatively popular, at least among higher-end phones. One of the major selling points of channel sounding is that it does not require specialized radio hardware because it uses similar frequencies and similar modulation to existing forms of Bluetooth with Bluetooth Low Energy and Bluetooth Classic. Oftentimes, with minimal modifications, you can build on top of the same radio hardware and add this functionality for minimal additional cost. And so you're starting to see this implemented in just about all new Bluetooth radio chips that are coming out. Historically, the way people were figuring out how far Bluetooth devices are from each other is based on the signal strength. But that is really not a great way for figuring out how far devices are from each other, because signal strength is hugely affected by a huge number of factors other than distance. Things like antenna directionality or obstacles in the way, or how multipath reflections are handled. All these things can result in big changes to the signal strength even when the distance between devices doesn't change. So while signal strength is usable for determining if a device is nearby or far away, if you want to get an actual distance, it's hard to get a usable, reasonably precise number from it at least in varied conditions, not just ideal line of sight situations. Another approach that's existed in the spec for a while is angle of arrival measurement, and you could use that for triangulation to find out where a device is and figure out distance from that. But this proved to not be a super popular approach, at least in common consumer applications, because it tends to require multiple antennas. The antennas tend to be rather bulky to have appropriate spacing between them, and if you're going to triangulate, you need multiple antenna arrays to figure out multiple angles of arrival so you can find the intersection and get a distance from that. And on top of that, both of these approaches are vulnerable to relay attacks. So there's nothing in either of these approaches that prevents an attacker from spoofing a legitimate device and retransmitting the same signals. So there was a need to have a relay-resistant approach to figuring out devices' distance from each other. For secure ranging schemes, the goal is to prevent devices from appearing closer together than they really are. And this is achieved based on the time of flight for signals, which is based on speed of light. In a secure ranging scheme, devices will exchange information such that an attacker cannot guess what the correct value to transmit is until the actual legitimate device transmits the right value, and then the attacker will be able to see it. So an attacker could extend the perceived distance by trying to block receipt of a message transmitted by the legitimate device and then replaying it at a later time, but the attacker would not be able to guess the correct value to transmit early to make devices seem closer together than they really are. For a simple secure ranging protocol, you could think of it like this. Imagine there are two devices we call device A and device B, and they both have a shared secret. Let's say both device A and B compute a pseudo-random value using their shared secret, and device A sends a ping message containing this pseudo-random value. If device B receives a ping with the correct pseudo-random value, then at a fixed time offset after when it receives the ping, it can send a response back with another pseudo-random value that both devices would know based on the shared secret, but an attacker wouldn't be able to guess. So then once device A gets back the response to its ping, it can look at the time between when it received the pong and when it sent the ping and subtract the fixed turnaround time at the other end. And what's left is the time of flight for the round trip. Then you can just use the speed of light to compute the distance between the two devices. Bluetooth channel sounding makes use of this approach in what it calls packet-based ranging. This is what Bluetooth channel sounding calls mode 1 for ranging steps. There is a second mechanism that channel sounding also makes use of, which is multi-carrier phase-based ranging. And what's done there is that it measures the round-trip phase shift and change in signal amplitude at multiple frequencies within the 2.4 gigahertz ISM band. This approach allows achieving higher precision than packet-based ranging for distance estimates, but it's harder to achieve the same level of security because the tones that are sent for phase-based ranging don't contain the same amount of pseudo-random information in there. There's also a mode in channel sounding for ranging steps called mode 3, which is essentially doing both mode 1 and mode 2 in a single step, where it sends both a packet and a tone in both directions. Now, while the spec defines these different modes for ranging operations for ranging steps, the Bluetooth spec does not tell implementers how all these different data points should be combined to estimate distance. And it leaves it flexible for vendors to implement. This is a way vendors can distinguish themselves from each other, but it also creates room for weak implementations. At the physical layer, there are 72 radio channels used for channel sounding, which range from 2404 to 2478 megahertz. They're all 1 megahertz apart. However, the channel range is not fully contiguous. There is a gap in the middle for the Bluetooth advertising channel 38. The frequencies used by advertising channels 37 and 39 are also skipped, since those are at the two ends of the 2.4 gigahertz ISM band. This is notable just in that the frequencies are not all contiguous, and the impacts of this I'll get into a little later. For packets, they can use either the 1 megabit per second or 2 megabit per second phi. That's the number of symbols per second in there. The phi works pretty similar to just regular Bluetooth low energy. The only difference is there's slight differences to the deviation of the modulation. For phase-based ranging, it just transmits unmodulated tones at these frequencies at certain times. There is a portion of the tone where transmission depends on a pseudorandom bit. That portion of the tone may or may not be transmitted depending on the value, so you can think of that piece as an on-off keyed portion of the tone. Next, I'll go into explaining how packet-based ranging works in a little more detail in channel sounding. For this round-trip exchange, there is a packet type called the CS sync packet. CS sync packets all begin in a manner very similar to other Bluetooth Low Energy packets with a preamble that'll be just alternating zeros and ones. After that, there's an access address. In channel sounding, the access address is a pseudo-random value generated based on the shared secret, and it changes for every single packet. It's not just consistent for a connection the way it is in regular Bluetooth LE. Optionally, after the access address in the 4-bit trailer, which is fixed, you can have another 32 to 128-bit sequence of bits that's either partially or fully random. For the sounding sequence, which is a partially random form of trailer there, it's either 32 bits or 96 bits, and it's mostly just alternating ones and zeros. However, there is a field within that sequence that's called a marker that can be either 0011 or 1100. Those are the two possible polarities for it. And the position, both the position and the polarity of the marker is randomized. For the 96-bit sequences, you could have either one or two markers in there, just depending on another random value. For the random sequence option, they can range from 32 to 128 bits, and they're just fully random. So these serve two purposes. One is just adding more random information or pseudo-random information into the packet to make it harder to guess the correct value. And secondly, by making the packet longer, it may be easier to measure the timing of the packet more precisely. The security of channel sounding is mostly built around an AES-based pseudo-random number generator. You have a key exchange happen earlier. That's sort of outside the scope of channel sounding itself. And then there are a lot of different things that are dependent on the outputs of the pseudo-random number generator. For packets, there is always the access address, which is 32 bits, and then you have either the sounding or random sequence, which can range from either nothing, 0 bits, up to 128 bits. So combined, you could have anywhere from 32 to 160 pseudo-random bits that an attacker would need to guess within a packet. And this is a good number of bits that's relatively unlikely to be guessed correctly within a small number of attempts. Generally, if you have multiple failures, then the connection will fail. So it's not like you can brute force through millions of possible access addresses and try to get it right. The connection will just not work. For phase-based ranging, there is a lot less pseudo-random information in there. There is just the extension slot, which is a time slot where there either is a tone or isn't a tone based on a pseudo-random value. This is just one bit of entropy for each ranging step. Now, within a typical ranging operation, you'll have multiple ranging steps. I've seen, say, implementations choose 8 steps or 10 steps or 20 steps. These are sort of typical numbers of ranging steps. So even for phase-based ranging, to get all of them correct, you need to guess correctly all, say, 8 or 10 or 20 times. But still, it's more feasible to guess them correctly compared to for packet-based ranging. There's also a pseudo-random channel hopping sequence. Unlike regular Bluetooth LE, in channel sounding, the hop sequence is again based on the AES-based pseudo-random number generator. So just by observing past hops, you can't figure out what the actual key is from there. For packet-based ranging, there's also a thing defined in the spec for trying to detect if someone is tampering with the signals to try to make the packet receipt time appear earlier than it should really be. This is an optional feature in the spec, which I'll get into a little later. Now, assuming the key exchange happens securely, which is a whole separate topic, the AES-based pseudo-random number generator is pretty standard and solid. But the interesting part is how these pseudo-random bits are being used to provide security to the ranging operations. For the channel hopping, in my opinion, I consider it a near zero security feature beyond just making the implementation of attacks slightly more of a pain, because an attacker could just use a wideband radio or multiple radios to listen in all channels and transmit in all channels at once. Typical low-cost radios just are able to tune to one channel at a time, but if you're using a wideband SDR or just a bunch of radios together, it's not a problem. So that I don't consider security. The crudest form of attacking round-trip time measurement is just having an attacker respond to a ping message early. If it weren't for all the pseudo-random fields in there, then an attacker could just receive a ping and send back a pong, and if that attacker didn't need to correctly guess all those values, then the original device A that sent the initial ping would receive an early pong and think the device is nearby. But channel sounding is designed to defend against this type of attack in packet-based ranging, since there are all these pseudo-random values within what's being sent back. Now, there are more sophisticated attacks that can be used to tamper with the perceived packet receipt time. One of the most notable is something called the early detect, late commit attack. And the idea with it is that you start, as an attacker, you start sending a response early even though you don't know what the correct bits should be. And you start sending, you send a predictable preamble at early, and then once the unknown data starts to be sent, you send ambiguous waveforms initially. And then, partway through the symbol, once you find out from the legitimate device what the correct value for that symbol should be, partway through transmitting the symbol, you change what you're transmitting so that the receiver perceives what you sent as the correct symbol value in the end, or the full duration of the symbol. So this allows allows the receiver to think that the packet started arriving earlier than it really did. Here's a little example of what an EDLC waveform could look like. Let's say the legitimate packet, we start off with a preamble of just 101010, similar to what's in a Bluetooth packet. And then we have some value that is unknown to an attacker and pseudo-random. An attacker could start sending a preamble a little bit early. In this example, the attacker's preamble starts half a symbol period early. And then once the actual data starts, the waveform the attacker is sending is just an ambiguous runt pulse that could go either way. And then once the attacker finds out what the correct value for that symbol is by listening to the legitimate attacker, then the attacker changes what they're transmitting. So that if you look at the average value over the entire symbol period in the attacker's waveform, the average value is the correct value that matches what the legitimate signal is. And so the receiver, because it uses the preamble to synchronize when it's receiving and determine the packet arrival time, this can fool many receivers into thinking a packet arrived a fraction of a symbol period earlier than when it really came. The normalized attack detector metric is a feature defined in the spec to try to detect these kinds of attacks. This is a feature meant for packet-based ranging, where it looks at two different things, at least based on the spec's guidance. The spec allows implementers to do whatever they want, but it at least suggests two possible approaches. One is cross-correlating the received signal to the expected signal, and I'm talking about cross-correlating the actual raw IQ samples before you're doing all the demodulation, get the digital data out of it. If the signal seems distorted more than some expected amount, then that suggests maybe something fishy is going on. Another thing it suggests doing is performing frequency domain analysis of the received raw signal and looking for anomalous peaks at harmonics of the symbol rate that are also typically associated with these early detect, late commit attacks. And the spec says that for a device to be implementing NADM, it needs to achieve 90% or better reliability in detecting certain predefined test cases. Now, it's important noting that NADM is an optional feature, and having looked at a bunch of popular implementation, today nobody implemented it. So it's kind of moot right now, and I can't really analyze its effectiveness if there are no implementations for me to actually look at. So going over packet-based ranging in general, the benefit is that with all these pseudo-random bits in there, it's hard to spoof a packet and guess all the random bits correctly. But the issue with it is that the precision you can achieve in timing and so distance estimates is quite limited. Because of the narrow channel bandwidth, it's hard to get a very precise estimate of when a packet starts. With ultra-wideband, you have hundreds of megahertz or gigahertz of bandwidth in there because they're super wide pulses, super wide band pulses that are super narrow in time. Here, it's much a little more fuzzy in when the actual start of a packet is. And for that reason, the clocks that are sampling the signals are also generally relatively slow. I've seen 4 megahertz is something typical for these. So if you're sampling at 4 megahertz, then your packet timestamp precision is just 250 nanoseconds. And in that time, light travels 75 meters. So even if you're looking at round trip time and you're halving that, that's 1 bit of information has 37.5 meters difference in distance. And that's huge. That could be you're right beside your car, or your phone is a few houses away from your car. And that's almost unusable for a lot of applications that are security critical. So there's a need for something that gives better precision. That's where phase-based ranging comes in. In multi-carrier phase-based ranging, you measure the phase shift and change in amplitude for round trips at multiple frequencies. So you have 2 devices, let's call them an initiator and a reflector. The initiator sends a tone, the reflector measures the phase of the tone relative to its own local oscillator, and then the reflector sends a tone and the initiator measures it relative to its own local oscillator. And then they exchange the measured phases and signal amplitudes at both ends. And from that, you can determine the round trip change in signal phase and amplitude. And if you do this across a bunch of frequencies, you can also build a frequency response for the channel. One thing to note is that in real devices, the clocks will not be perfectly synchronized. There'll be small differences in the crystals and inaccuracies in there. So the spec handles that by having an additional mode called mode 0, where it measures the frequency offset between the 2 devices and then compensates for it in software afterwards. For multi-carrier phase-based ranging, the key idea is that if you plot phase shift versus frequency at different frequencies, you'll get a line whose slope is dependent on the delay for the time of flight. And the greater the delay, the steeper the slope would be. This is an important approach because if you are just measuring the phase shift for a single ranging step, it's possible that the phase shift is a multiple of 360 degrees. And so you can't just rely on a single measurement if the phase shift's a multiple and wraps around. Whereas with this approach, by looking at the slope and just making many measurements, from the slope you can more reliably estimate the distance between devices based on the round-trip propagation time. 4 channel sounding, tones are sent, and the length of the tone is based on the number of antenna paths that are being measured. Usually there's just 1 antenna path in place, but the spec allows for multiple antenna paths if you want to do things like angle of arrival estimation. And the duration of the tone is also dependent on whether or not a tone should be transmitted during a time slot called the extension slot. So that's pseudo-random, and there may be something in the extension slot, there may not be, but that extension time slot is always there. It's just there may be a signal or may not be. For the security in channels in the phase-based ranging, the extension slot is one of the key features in there, as whether or not there is a tone in that slot is dependent on the pseudo-random number generator. And while it's relatively easy to guess correctly for a single step, since it's just a 50-50 coin toss, for multiple steps, then you're gradually making the difficulty harder. When there is, if a receiver sees a tone in an extension slot where there shouldn't be, it can know that someone is transmitting when they shouldn't be, and maybe there's some tampering going on. Likewise, if there's supposed to be a tone in an extension slot and there isn't, or if the tone in the extension slot has a different amplitude and phase than the tone right before the extension slot, then you would know that an attacker should have been transmitting an interfering tone when they weren't, and that could be a sign of an attack. While the polluted spec defines this whole extension slot feature, the spec doesn't say what you're supposed to do with extension slots, and this leads to a problem. So with tones, it's relatively simple for an attacker to manipulate the tone at the receiver. So let's say we have a legitimate signal, the blue one on top, and we want to shift the phase of what the receiver sees. We just need to add our own interfering tone at the same frequency, and we can pick the amplitude and phase of our interfering tone appropriately to get whatever phase and whatever magnitude we want at the receiver. We can plan for constructive interference or destructive interference and adjust the phase arbitrarily through that. Now, for channel sounding, they try to defend against this through these extension slots and also through the pseudorandom channel hopping, though, again, with the channel hopping, you could interfere in all the channels, so that's not a big defense. It's the extension slot that's really the main defense here. But since the extension slot handling is not defined by the spec, while it could be used to detect spoofing, the spec doesn't mandate it, and so implementers just chose to do nothing. If the spec doesn't say I need to do anything, then why should I? Just less work. So because of that, I don't really consider phase-based ranging and channel sounding to be secure ranging, despite how channel sounding is marketed. There's one other aspect of the technology I want to dig into, which is how multipath propagation impacts it and how that impacts the security of it as well. So for those who are not familiar with multipath propagation, when you transmit a radio signal, it doesn't always just follow a direct line of sight to the destination. Some of it may go in a direct line, but some of it may bounce off walls or other obstacles. Some of it may even curve around mediums. Some of it may be focused by something like the way, say, a satellite dish does. And so when you're receiving a signal, if you see multiple paths that the signal came, the strongest path might not even be the shortest path. And if you're trying to determine the distance between devices, you want to find what is the shortest path, the most direct path for a signal to reach you. So you need a way to overcome the confusion in arrival time estimates that the multipath propagation causes. Here's a little example of what multipath propagation would do to a pulse. So let's say we're sending 3 pulses like this, and there are 3 different paths with different delays and different signal strengths that are in the radio channel. Then what the receiver will see is a superposition of all the different paths. And the receiver will see some confusing tone where the actual time of the shortest path is somewhat ambiguous until you break it down. When you're doing multi-carrier phase-based ranging, there is a way you can unentangle this. So if we're measuring the amplitude and phase shift for the round trip at multiple frequencies, while individual paths, let's say the individual paths always have the same signal strength in themselves, and the phase shift follows a consistent line, when you're combining multiple paths, you end up with these curves in the phase and oscillations in the amplitude as you vary the frequency. And through this, if you go back to, say, a signal processing class in university, you'll remember that the inverse Fourier transform will yield the impulse response from a frequency response. And so we can use this to figure out what are the delays of the multiple paths through looking at the impulse response. So here's a little example of this, where we took those same 2 paths and the combined path that has this oscillation in amplitude as we change frequency and that curvy variation in phase. If we take this and just do an inverse FFT of the data over this band we captured from 2.4 to 2.5 gigahertz, and we zoom in on the early portion of that inverse FFT, we'll see 2 peaks here, and these 2 peaks represent the 2 different paths. So if you do an inverse FFT and then look for the first peak in that data, that should be the earliest path, at least in a fairly clean, simple world. Now, in channel sounding in practice, usually you don't take measurements at every single channel. And on top of that, the channels used for phase measurement in channel sounding are not even contiguous. There are gaps in them. So you'll inherently have sparsity in your measured frequency response. In a lot of implementations, they may only measure, say, 8 channels that are spread out some random spacing apart. But while this worsens the quality of the impulse response, you can recover from it, it's still usable. If you take these sparse measurements and zero pad them in the frequency response so they're all in the right position in the array, and then take an inverse FFT of that, you'll still get a sort of usable impulse response. And generally, the peaks will still roughly correspond to the correct associated paths. However, if you're reducing the number of measurements you're taking, that reduces the number of measurements an attacker would need to successfully spoof to induce a false peak in the impulse response. And if you have a false early peak in the impulse response, then the algorithm will think there is a shorter path and will report the distance is closer than it should really be. So here's an example of this. The blue circles represent different sparse points I randomly selected for sampling. This is with 10 points sampled, and then I zero padded the data in between these samples and then took an inverse FFT for that and then compensated the magnitude as well just for the sparsity. And so you see that the dashed line is the inverse FFT of the sparse data, and it still has peaks in roughly the right places, but it's a little bit noisy and distorted. And you have a sort of false early peak at zero delay in there as well. You can make your algorithm reject early peaks at zero delay, for example, but in general, the sparsity worsens the quality of measurements, and sometimes just because of this random sampling, you get false peaks that shouldn't exist, just that are noise, and it just makes the performance worse, but in terms of accuracy. But if you reduce the number of measurements you need to take, then you can be more quick in determining the distance between things and have a quicker update rate. Now, there are other approaches that are better than the inverse FFT of the sparse frequency response. One of the most notable is something called the multiple signal classification algorithm. And the idea there is that you create a model of how the delays impact the signal, and you treat the different measurements as a different sensor. So with your model, you can predict what should be measured at the different frequencies you're measuring at if the delays were as such. And then you essentially do some optimization to find the delays that best match the measured data. So this approach handles sparsity in the measurements much better. And secondly, it allows achieving significantly better precision than what the inverse Fourier transform does in timing. So this is what a lot of implementations are using to get more precise timing estimates. There's also another approach that's used by some vendors, which is using neural networks to process the data, because in the real world, there are all sorts of strange phenomena that are hard to model, and just modeling everything as just multipath delays with a different amplitude and different delay is often not enough to model real-life situations. And so companies have trained neural networks just on data that they've captured in a wide range of different environments, and these can be more robust against just varied RF environments. But the issue with this is that it's hard to reason about how a neural network is making its decisions. And so it's a bit difficult to analyze how they would behave in an adversarial situation, and it could be an interesting area to research further. So wrapping this all up, with these two different ranging methods, the phase-based ranging and the packet-based ranging, the core specification doesn't say how you're supposed to combine these two measurements. And it's left open to implementers. Now you have more precise but less secure phase measurement and a less precise but more secure packet round-trip time-based measurement. When combining them, what I saw implementations are doing is either they present both and people will just use the phase-based ranging because that's the only one with the usable precision, or they just prioritize the phase-based ranging and either don't bother with the round-trip time or discard that measurement when phase-based ranging measurements were looking of good enough quality. So with that, the security that's present in the phase-based ranging is kind of moot if your implementation just throws all that away and prioritizes the phase-based ranging. And so if you're just throwing away the security of the packet-based ranging with this, and the phase-based ranging doesn't even have validation of the extension slots, then it's not really secure ranging as is. So I examined a bunch of different vendor implementations from TI, Nordic, NXP, and Scilabs. None of them implemented the normalized attack detector metric. All of them support phase-based ranging, and most of them rely on that as their main approach for ranging. For packet-based ranging, TI didn't even bother implementing it as they felt the accuracy of it or the precision of it is useless. Nordic, NXP, and Scilabs implemented it, but they don't prioritize it. For the Nordic SDK, when both measurements are available, it just returns the phase-based ranging number. For the Scilabs SDK, it defaults to just enabling phase-based ranging. It doesn't enable packet-based ranging by default, or it doesn't prioritize that. For NXP's SDK, they return both numbers. The SDK presents both as equally valid, but users will generally just use a phase-based ranging number because that's the only one that's reasonably precise. None of these implementations had anything in place to cross-validate the phase-based ranging distance estimate and the packet-based ranging distance estimate. They just give two estimates or just prioritize one and don't make sure that the two seem roughly in the same ballpark. So again, that's rendering all the security of packet-based ranging moot. And for the phase-based ranging, none of them do anything with the extension slot data. They measure it. They measure the tone, phase, and signal strength in the extension slot, and they indicate in data at the HCI layer whether or not a tone should have been present in that slot. But then higher levels of the stack that actually process that data to get a distance estimate just completely discard all the extension slot information. So you're not getting any security out of this extension slot in these implementations. As for the algorithms that they use for processing the multi-carrier phase-based ranging data, TI has the biggest variety of options there. They have both the simple inverse Fourier transfer approach, but they also had music and neural net-based approaches, and as well as a mechanism to try to automatically pick between which is most suitable for the current environment based on some additional analysis of the data. Nordic's was relatively simplistic. They had both a naive phase slope estimation approach as well as an inverse Fourier transform for the multipath handling. NXP had implemented both the inverse Fourier transform approach as well as music, and Scilabs did music and the neural net approach. So altogether, channel sounding has the building blocks to create a secure ranging system, but the spec is too flexible and it allows vendors to implement things that are insecure. And when vendors have the choice to make their system faster and simpler to implement, it's cheaper for them, and there's enough marketing materials making Bluetooth channel sounding sound secure, and so they just follow the easiest path, the path of least resistance. Vendors are choosing to use small numbers of ranging steps. They're choosing to just prioritize phase-based ranging and not really do anything with packet-based ranging because getting precise distances from that is hard without more hardware work. They don't bother implementing NADM because it's more work to implement and more complicated. And they don't do anything with extension slots because the spec doesn't mandate they do anything. And so you end up with something that just doesn't really provide much security. There are some interesting areas for future research. One is actually implementing the phase-based ranging attacks. In principle, it should be fully doable. In practice, some of the challenges are precisely timing when you're injecting your interference, as well as putting out the correct signal phase for interference, given there's unpredictability in the oscillator, in the phase of each of the oscillators at the different frequencies. So it's something I want to experiment with some more, and I'm working on. But aside from that, implementing an early detect, late commit attack would be quite interesting. People have done it against other protocols, but given nobody's doing NADM, if someone implements an EDLC attack against it, maybe vendors will finally feel incentivized to bother implementing NADM. And also for looking at these music-based and neural network-based algorithms, it would be interesting to experiment with ways you could get them to report early shortest paths with minimal tampering with measurements. Could be an interesting chance for sort of adversarial neural network design. Seems like an interesting topic to me. So, thank you.